Hello, I'm Bas Coppus, the Communication Manager of Group 6 of the OGO Energy Challenge project. I will give you a short introduction about the content and aims of this project. The case. The project is hosted by research group EPE, which stands for Electromagnetics and Power Electronics. Next to EPE, we also have EPE Vehicles, which is a car manufacturer that produces different types of passenger cars, and they have recently designed their the first version of their fully electric car. However, their chief technical officer also has decided to produce a scaled down version of the new model for testing purposes. And because EP Vehicles doesn't have much knowledge about the technology of electrically driven cars, they decided to start a partnership with the TU Eindhoven, and this resulted into the OGO Energy project. The OGO Energy Challenge project, the main selling point of the car, the top selling point, is the energy consumption. Every research group gets its own version of the model car, and the project is a competition between all the rival research groups, and they all try to find the best overall solution to the problem. So the aim of the project is to develop and demonstrate a driving strategy that yields minimal energy consumption for the model car. We hope that the results of our study will provide data which the CTO of EV vehicles can use to improve the car, and for the conditions in which it will normally be used. So we try to make the data as realistic as possible, and we hope it will also be able to support the owner of the car to minimize the energy consumption and inform them about good driving practices. The project setup, well, as it's a huge project, we decided to divide our group into 4 different departments, all consisting of 2 people. This was profitable because every different department could specialize on his own task instead of working with the whole group on everything, because then we would get a very non-detailed study and it would be very general. Also, because the departments, faster communication is possible, and also faster decision making, as otherwise you have to discuss everything with the whole group, and now every department can discuss the problems they have between 2 people, and yeah, it's just a faster way. You work more efficient in the decision making. We also have weekly meetings in which we discuss in which every different department presents the progress they made in that recent week, and also present what they are going to do in the next week. This is so everyone can see the progress of the different departments and see whether they keep up with the schedule and don't fall behind. And it's also a motivation for everyone to do his best for the group, and everyone has the same goal, so everyone will do the best as he can. Then the content of this presentation, we'll first talk about the tank-to-wheel analysis, which is an analysis that shows the overall energy losses in the different parts of the car, and also from the car overall, and also the total energy consumption. The tank-to-wheel analysis can be made with the results of different tests we are going to do. We're going to do the dynamometer test, the rolling resistance test, and the wind tunnel test for the air drag. And the tests will be performed by 2 departments, so there's a group of 4 people working on all the tests. Then, in addition to this analysis, there's another department working on the communication systems in the car. The model car has to be able to work with a highway toll payment system, because it has to pay toll by itself every time it crosses the finish line. So every lap it has to pay toll one time. And this is programmed using an infrared sensor. Then we have the fourth department that works on the speed regulation sensors. They work with a speedometer and LED system. This shows the speed we're driving at, and it helps so the driver will be able to see at which speed he has to drive to drive in the most efficient way. And there's also after this we will make a driving strategy for the driver. However, we cannot tell anything about that yet because we need the results of the tests we're going to do to determine the driving strategy. So when we've obtained those results, we will try to make a good driving strategy for the driver. Then we'll first look at the dynamometer test presented by Thomas van Bodegraven of the Dynamo department.
Hello, I'm Thomas van Bodegraven, and together with Teun Dobbelsteen, we are responsible for the dynamometer test and the test plan. So the purpose of this plan is to determine the power losses in a powertrain. The vehicle has a powertrain. That means you go from the electric motor up until the wheels, and there are different parts in them that don't have 100% efficiency. That means that in every part there is a little bit lost, and we can determine those with 3 experiments we did. The first one is no load measurement, the cockwheel removed from the motor. Second one is the motor is connected to the battery and it will just ride. And the third one is the motor connected but it will have 0 speed. And I will also tell a little bit about MATLAB, which is also involved in this experiment. So the first experiment or test is with the motor cockwheel removed. This means that the only parts involved that have not 100% efficiency in the car are the gears, and there's also rolling resistance, which causes some power losses too. So the vehicle is placed with the rear wheels on the dynamometer. We have a roller attached or connected to them, or they have a surface contact. We can, with the code of MATLAB, which I will elaborate further, we can control the forces and the velocity, and thus we can input some power with the rollers. And since the power only gets divided by the rolling resistance and gears, we can determine the rolling resistance and gears power losses with this test. The second one, we will connect the motor to this one, and now all the power losses are visible, or the whole powertrain is rolling. So we have the motor that has some power losses because it's not 100% efficient. We have the auxiliary losses, for example the fan in the car. We have also the gears and of course the rolling resistance. We also take part in this experiment. The last one, this one is also with the motor, but now we have 0 speed. So this means there is no, the gears aren't running, and the only thing that is, or the power losses are in this experiment, the auxiliary losses. So we can determine these instantly from the results of the power from the roller. And if we do all these 3 tests, we can just derive all the power losses, and we know the power of the battery, and when we subtract these power losses, we can know how much power is delivered to the wheels. So how we do this is we complete a program, or my team mate Teun did this. You can see here the distance is traveled, the velocity and the forces that's exerted on the roller. So at first there is 0 distance, and it will go to 2.5 meters per second, and then 5 Newton is exerted, and this will continue until we reach the next distance. So after this we have a lot of data points which we can interpolate if you want all the specific lines. And another person in our team, or who was working on our team, that helped us was Thomas. He made an estimate about the values for how it should be. So here you have a line of the rolling resistance, which is going down a little bit, and here you have the line of the air drag. So this is a nice estimate of how it's going to be and how it should be. So the teamwork I had with Teun was great. We had a good distribution of work. We were always working on something. So as I said, Teun did the MATLAB things on the MATLAB, and I worked on the 3 experiments, and together we formulated a test plan. This went well, and although our test plan did not get approved, this was not a big issue because the main errors were minor and we could fix it easily, so it was not a big deal, and I think we did a good job. So our future agenda, what we are going to do now is I'm going to still work with the same team, so still with Teun. Up until now we were on schedule, we finished everything and on the test plan. What we are going to do now, because we're still in week 3, we have a lot of weeks left. Teun and I are going to do the driving strategy, when we have all the experiments done and we can make a good estimate about the driving strategy. And then after that we can help others and formulate the final report with each other. So now Bas is going to tell us something about the other 2 experiments.
Yeah, so then we'll move on to the rolling resistance test. The rolling resistance force is a resistive force acting on the car, which is caused by the friction between the tires of the model car and the road surface. The aim of the experiment is to find the rolling resistance force and its coefficient. The model car will be pushed in a forward direction on a surface with a slope of 0, and we will let the car coast down until it stops. We'll also put measuring tape on the ground so we can see what distance it takes for the car to slow down, to bring the car to a stop. And we'll also put a line on the ground from where we release the car after pushing it. The variables that will be measured are the velocity and time, and they will be stored on a SD card. The experiment will be performed with the electromotor friction taken into account and without. For the first test we will take it into account, and then a cogwheel on the electromotor will be removed and the electromotor friction won't be taken into account. So from this we can also determine the electromotor friction in addition. Then how will we calculate the rolling resistance? From the obtained results, the velocity and time, we can calculate the average acceleration. With the average acceleration, we can use the formula F is m times a, so we use the acceleration and the mass of the car to calculate the total force that the car needs to overcome. However, because the rolling resistance force is a resistive force, it will have a minus sign as it's working against the car. The aerodynamic drag force also has an influence on the car during the rolling resistance test. So you have to subtract this one from the total force and you'll get the rolling resistance force. And then having the rolling resistance force, the rolling resistance coefficient can be calculated using the formula that the rolling resistance force is the rolling resistance coefficient times the normal force. And as the rolling resistance force has a negative sign, you would say that the rolling resistance coefficient will also be negative. However, this is not the case. And you can also we can also calculate the electromotive friction by subtracting the total force excluding the cogwheel from the total force including the cogwheel. Then something about the wind tunnel test for the air drag. The aim of the wind tunnel test is to determine the air drag coefficient belonging to the model car, and the air circulates through ducts of different sizes and shapes, and the total air pressure along the duct decreases with the inflow direction. The motor and fan are there to compensate this loss of pressure and to maintain a constant air pressure at the beginning of each cycle. There's also an opening in the wind tunnel, so static pressure within the wind tunnel is the same as the air pressure from outside the wind tunnel. In the test section, the car is placed on a rectangular platform with a force sensor attached to it on the front side. It hangs above the surface, so it doesn't have rolling resistance. And when the airflow moves the platform, the force on the force sensor will increase. The airspeed of the wind tunnel can be adjusted, and also the difference in air pressure will be measured by the wind tunnel. The test will be performed using different modifications of the car, sometimes with or without splitter and sometimes with or without spoiler. For all 4 possible modifications, the test will be performed at 4 different speeds. And how will we calculate the air drag coefficient? Well, from the equation of Bernoulli, it says that the total air pressure is the static air pressure plus rho times v squared, the air density times v squared divided by 2. From this, we can derive that the airspeed is the square root of 2 times the difference in air pressure, which will be measured by the wind tunnel, divided by the air density. And in this case, we can assume that the velocity is 1.28 times the square root of the difference in air pressure. Then the formula of the air drag force, which is this one, you can see the air drag coefficient is in it, and from that equation we can derive the equation for the air drag coefficient, which gives us that the air drag coefficient is 2 times the air drag force, which will be measured by the wind tunnel, divided by the air density times the frontal area of the model car times the velocity squared. And just a quick reflection, the teamwork went great until now. I'm working with Bart-Jan, and we finished everything on time, and now we handed in our second iteration for the test plans, and we think they'll both be accepted. And then next week we're going to perform the tests, and when the tests have been performed, test reports will be written, and we'll also try to come up with a optimal driving strategy for the driver, and and at last the final report will be written as well. So then we move on to a part about the communication systems in the model car, presented by Zhengyang Lu.
Hi, I'm Zhengyang Lu. I was responsible for the communication system, the time payment system. So in week 1, I got an understanding of the task, what I have to do, what is expected. And then I set up Arduino IDE for coding. It was my first time working with Arduino. And then figure out how the IR and the IR sensor codes work to actually use them for the system. So essentially what I had to do is create a wireless lap counter using IR and radio signals. Also have to assemble the IR receiver, just have to program the radio transceiver because it's already mounted onto the Arduino board. Then have to create a program that implement these components. So here's the flowchart for the lap counter program. So first the program starts, it starts detecting IR signals. When it doesn't detect the IR signal, the loop keeps going. When it does detect an IR signal, it checks if it is the desired one, and the desired IR signal sent by the IR transmitter at the track will be exactly 2 bits long and with value of 1. If it's not the desired IR signal, it goes back to detecting for IR signals, and this is another loop. If it is the desired IR signal, then it tells the radio transmitter, the radio transceiver, to send the vehicle number to the specified radio receiver at the track. So basically, every time the car crosses the finish line, it sends the car number to the computer. So it counts the lap time and number of laps. After this, the program waits 10 seconds before detecting for IR signals again. This is to prevent our car from detecting the IR signal twice, but when crossing the finish line only once. This could happen if the vehicle is moving a bit slow or some other problems. That's the overview of the program. So in week 2, I first coded the IR receiver. I've actually since Niels brought his own Arduino board with an IR sensor, which was the exact same model as the one we were supposed to use. I used his IR sensor and played around with the functions, with the library functions, got an understanding of how it works, and finished coding it, tested on his sensor again to make sure it really works, and then viewed some tutorials online to figure out how that radio transmitter works, and what are the library functions, how they work, and such. And then I finished coding that, and then we tested the radio transmitter on the actual car at the soldering lab. So we made sure the radio transmitter works, and then we combined me, Bart, and Niels, the 3 of us. We combined both the IR part and the radio transmitter part, and then tested it again to make sure it all works in combination. Also have, as I said before, I had to assemble the IR receiver. This is a generic overview of how the receiver has to be connected. This is just an overview because the actual component has different pin layout, as you can see here. And with some help, I made a scheme with the actual components. So these are the 3 pins from the IR sensor, and I have to wire the pins to this components, which is this, and a cable from the Arduino box on the car will be connected here, and then I have to solder everything so that it's all stuck in place and would not move. Some challenges that I faced took some time to figure out how Arduino coding works. It was my first time doing it. I also don't have many soldering experiences, but I managed to overcome it with minor helps. Figuring out how the the IR receiver is connected also took some time. It was a bit confusing at first, but I managed to overcome it. And another big problem was the pin layout. We kept writing the wrong pin number on the program, which caused some issues, but at the end we managed to figure out on which pins we are supposed to use for which components on the Arduino board. And overall, I think my progress is quite good. Worked well with my two other colleagues and the rest of the team. I'm quite ahead of schedule because I was able to work in parallel instead of waiting for Niels and Bart to finish their part, and then I programmed my part. So that was that was very efficient. What I will do in the future, since I'm already finished with my part, is that I will create a detailed outline for the report, so that when everyone is done and they're ready to write the report, they know exactly what to write. There is a coherent, logical structure, and which makes everything more efficient. And in week 5 and 6, there will be actual coin payment system checks to check that the system works perfectly. Thank you.
I'm Niels Veenstra.
Hoi, goed zo bij deze ruimte.
We zijn nu over deze chapter daar. Okay, I'm Niels Veenstra, and together with Bart I made the speed and light system. The system consists of two main parts, the RPM sensor and the LED strips. With the RPM sensor we can calculate the speed of the vehicle, and with the LED strips we can show if the driver is driving the ideal speed or not. The speedometer system, we made an interrupt function, and it triggers every time the RPM has a rising pulse. So every time the magnet is near the RPM sensor, this function is triggered. What we do, we measure the time with the micros function, and then with that we can calculate the difference between this interrupt and the one before, and by that we can calculate the speed of the vehicle and the distance that it traveled, and then we can and at the last we store the time as the last time, so for the next iteration it also has the most recent time. And then we have the LED system. Each LED strip is made of 32 RGB LEDs, all connected to shift registers. And we have an array with every LED, so and then we can calculate if the LED should be red, green or blue for the speeds, and then we write it to the LED strips. So every time we write one bit and toggle the clock, so it's stored in the shift register, and then we toggle the latch, so it's updated it's updating all the LEDs. And then some upcoming activities. We would like to implement the drive cycle we're going to do in the code, so that if we have a corner, for example, we can slow the car down and keep driving the most efficient strategy.
Yeah, then a short conclusion of the presentation. So everyone's up to date, which is fine. The test plans are almost accepted and will be performed next week. We will continue the weekly meetings, so everyone can still check on everyone whether they're up to date and will not fall behind. After the tests have been performed, the test reports will be written, and we'll make a start on the final report. Everyone who's doing something with programming are on scheme. They've finished almost everything. And also after the test plans, the driving strategy, optimal driving strategy will be.
En ik heb voor deze ruimte en ik moet een tutorles geven. Ja. Dus bij deze vraag of jullie gewoon
we zijn nu klaar, ja.
weg kunnen gaan. Alsjeblieft.
We zijn nu klaar.
Yes, top.
And then the optimal driving strategy will be determined. And thank you for your attention.